Hi there, Andrew Dunkley here, and you're listening to Space Nuts. It's a Q&A edition. This is where we take audience questions, we put them in a barrel, we pluck one out and we go, no, that's too hard, and we just keep doing that over and over again until we find 4 easy ones. Today, we've got questions about black hole evaporation. Simple. Earth's atmosphere, Artemis 2 and those moon meteorites that they witnessed. Somebody's thrown in a question about that, and missions to the sun. Don't forget your sunscreen. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to try and solve all of those little riddles is Professor Fred Watson, astronomer at large. Hello, Fred.
Good day, Andrew.
You can't say good morning or good afternoon or good evening because it might not be that when people listen to us.
On the other hand, it is a day. I could say good night. Yeah.
Yeah.
But anyway, it's certainly a day. Daytime here.
All is well with you, I assume?
Apparently.
Yep.
Still seem to have
That's a good answer.
I'm supposed to have, yes. Well, it can only be apparently because you never really know, do you? What's going on inside? What's going on outside? The things that you haven't found out about yet. Yes. No, all well so far.
I recently had a profile piece done by the Cancer Council in Australia for Men's Health Week because of what I've been dealing with the last 3.5 years. So to encourage men to go and get their PSA tests and get their, let's just say, junk checked out to make sure that they're free and clear. And I think it's a very important message. But one of the things I've learned through the treatment and discussions I've had over the last 3.5 years in regard to prostate cancer is that because I have now had it, there is a possibility that my 3 children have a 50% higher chance of developing it in their lives. So it's not just about you.
Yes, exactly.
It's not just about you as an individual. If you've got sons, it's about them too. So it makes it even more important to get tested.
Absolutely.
And you don't just have to be in Australia. This can happen to any male on the planet. So go and get that prostate test done for peace of mind. Lecture over. Let's deal with some questions, Fred. We will go to our first one. This is a pretty short and sweet one, but it's a complicated issue, really. Black holes are gaining mass if they are colder than the CMB. How much does this lengthen the time before they evaporate? That's a question from Bob.
So I'm interested in who this question has come from because I've got a very old friend by the name of Bob Argyle, which is the name on the email you sent me.
It is.
We worked together in the Royal Greenwich Observatory at a place called Herstmonceux Castle in the south of England in the early 70s. Now, Bob went to Cambridge and I think is still there. I wondered if there was any clue to his whereabouts in your email.
No, because what you see is what you get.
Okay. Anyway, well, if it's Bob, g'day, Bob. Good to hear from you. We should email one day. Yes. It's good to hear he's still going strong if it is. And if it's not, I apologize that I'm mixing you up with somebody else. But it's a great question. And it's one that I had to do some homework on before the show, and the bottom line is, first of all, what's the CMB? The cosmic microwave background. That is basically the flash of the Big Bang, which we still see. When that light was emitted, it was bright white light. As the universe has expanded, that radiation has expanded also. It's been stretched. The waves have been stretched into microwave waves. So we see this background of microwave light over the whole sky, and we can deduce lots of things from it. It corresponds to a time, I think it was about 380,000 years after the Big Bang, when the universe basically stopped being bright and a fog of radiation everywhere, which it was until that time. So that's the CMB. Now, what the CMB does is give space a temperature, and the temperature is 2.73 degrees Kelvin, degrees above absolute zero. And so that is, when you compare it with the temperature of a black hole, and we've discussed this before, Andrew, on the Q&As, black hole temperatures are very, very cold. Typically, a few tens of nanokelvin. That means a few tens of billions of a degree above absolute zero, compared with the 2.73 degrees. And so that temperature, what that means then is that photons of cosmic microwave background radiation can be added to the mass of a black hole, because the temperature of the black hole is colder than the temperature of the background radiation.
Yep.
So there is an issue, which is one that Bob raises. I've lost my question. Here it is. How much does this lengthen the time before they evaporate? So if you've got a situation, we know that black holes evaporate, the situation that was highlighted by Stephen Hawking back in the 70s. Black holes evaporate over very, very long periods of time. But what Bob's saying or asking is, does the fact that they're gaining mass because the cosmic microwave background is warmer than the black hole, does that extend this time significantly? I had to go to AI to answer this question, because it's got some very, very lengthy calculations. But the answer is, it's, well, as the AI tool I used says, it was practically negligible. Changing the final lifespan by less than 1 part in 10 to the power 50. So that is definitely negligible. And it's because of it's about the length of time that the cosmic microwave background radiation feeds the black hole. And it turns out that it's the black hole is effectively evaporating faster than the stuff that's feeding it. Yeah. And so it basically extends the life of the black hole by a very, very small amount indeed. There's plenty on the web about this if you really want to get into the nitty-gritty of it, but it is a really interesting question. One that I have to say, Andrew, had not occurred to me before. So I'm very glad that Bob has raised it, and I appreciate him doing that. And if it is you, Bob, I've still got your record of Das Rheingold in my record cabinet behind me, the one that you gave me back in 1973.
Well, he doesn't want it back.
No,
that's the other thing that's said in the email. Don't send that back. It's rubbish. No, I don't know. But maybe Bob could message us again just to confirm or deny.
Yes, I know nothing of Fred Watson. Yes.
Never met him. I don't want to.
Don't want to, no.
Oh, dear. The other interesting thing that comes from that is because of how cold a black hole is, if you get too close, you turn not only into spaghetti, but cold spaghetti. And that have you ever eaten that? It's horrible.
It's not nice. No, you're right. It's the worst of all worlds, isn't it?
Gosh, it just gets worse. These black holes are just starting to make things even more horrible.
Yeah.
Thanks, Bob. Great question, and thanks for sending it in, and we look forward to hearing from you again. Our next question, Fred, comes from Greg. Hello, Fred and Andrew. It's Greg from Minnesota. Coincidentally, Greg is the only Greg in Minnesota.
That's just as well
to believe. Maybe not. He says Titan is just a moon of Saturn. I mean, just a moon of Saturn. That's all it is. It's nothing important. Anyway, it has an atmosphere so thick that the pressure is 1.5 times Earth's. Venus is just a bit smaller than Earth, and its atmospheric pressure is 90 times Earth's, give or take. Does Earth have an unusually thin atmosphere for a rocky planet this size? If so, could our wispy atmosphere be because it all got blown away by Thea? Love the show. Thank you, Greg, the one and only Greg in Minnesota. That's a really interesting question. I've never really thought of Earth's atmosphere as maybe being,
thin and wispy.
But it generally is. When you look at photos of Earth from space and you identify the atmosphere, it makes you cringe a bit because you think, is that it? Is that all it is?
It is tiny. 10 kilometres, you're above 75% of it. It's scary in that regard. So that you're when you're in a jet, you're above most of the atmosphere. Quite extraordinary. It's thin and wispy, exactly as Greg says. So let's deal with these objects first. Titan. And yes, just a moon. It's the second largest moon in the solar system. It's bigger than the planet Mercury. But it does have about 1.5 times the atmospheric pressure of our own planet. And that's largely due to the difference in temperature between Earth and Titan. So Titan has temperatures, it's in the surface temperatures around about minus 180, minus 190 Celsius. And of course, that's cold enough for its surface to be solid ice, water ice, and to have liquid natural gas, ethane and methane, lakes on its surface, lakes and seas.
Yeah.
It's also got this very thick atmosphere. So the molecules of gas in Titan's atmosphere are very cold, and so they don't sort of bubble up to be, to get up to escape velocity, and so basically you've got an entrapment of this atmosphere of I think it's mostly nitrogen. Thinking about it. Actually, it is. Just checking a number here, it's 95% nitrogen, and the rest is methane and other hydrocarbons. So yes, it's got a nitrogen atmosphere, very, very cold, doesn't have enough energy to sort of disappear off into space, so its pressure is much higher than Earth. It's a similar story in regard to Venus, only kind of more so because with Venus, we have the situation that, excuse me, sorry, I've just killed the page I was looking at here, which is not what I wanted to do. Let me just bring it back. So
we've all been there, Fred. We've all done that. Yeah.
Yeah, so we've got a pressure. It's roughly 90 times Earth, which is kind of unbelievable. Why is that? It is because the atmosphere is mostly carbon dioxide, which is a dense gas. As you know, it's heavier than air. And so that basically increases the atmospheric pressure. We know that it's had this, runaway greenhouse effect because there is so much carbon in the atmosphere. And that's essentially the carbon dioxide traps the heat. You've got the runaway greenhouse effect, so you've got a surface temperature, which I think is in the region of 460 degrees Celsius. So the question, I guess the real nub of Greg's question is, why isn't the Earth like that? Was it all blown away by Thea? And the answer is probably not, but maybe in a way, because what keeps our atmosphere temperate is what's called the carbon cycle. It's the fact that we have, basically, we've got a planet whose surface is divided into tectonic plates. Those plates slide around one another, and you get volcanism, putting carbon into the atmosphere. That carbon sinks down and into the ocean, and eventually gets subsumed back underneath the continental plates. That's the mechanism. And that circulation of carbon acts as a kind of thermostat. It's what keeps the Earth's temperature reasonable. The reason why I said there might be a link with Theia is I guess it's possible that Theia had something to do with the origin of tectonic plates, although my understanding...
Okay. So not a direct correlation, but maybe something, an after effect.
Yes, that's right. The consequences. We've got tectonic plates which stabilize the atmosphere, and that might have something to do with Theia. Although my understanding of the Theia impact is that the Earth at that time was probably basically a magma world. It probably had a molten surface.
So would it have not had an atmosphere at all, or maybe just something really sinister and nasty?
Yeah, I think it had pretty nasty stuff in its atmosphere. There would have been an atmosphere there which was probably highly toxic and not good for future planet Earth. So it is that there could be a link with Theia. I suspect not. As I said, I think my understanding of the latest idea on the Theia impact is that the Earth had basically a magma ocean when the impact took place, and that's why the structure of the moon, the isotopes in the moon, are more related to the Earth's isotopes than what Theia might have had. We don't know what isotopic ratios there were on Theia. We don't know exactly what elements were there. But the moon is made of stuff largely similar to the Earth.
Okay. All right. But yes, we do live on a planet with a thin and wispy atmosphere, and we should do as much as we can to protect it.
Keep it there. That's
although you did, you gave me an idea. I mean, if carbon comes out of the volcanoes, goes back into the ocean, and then eventually gets sucked back down through the tectonic plates, we're not wrong to throw all our rubbish in the ocean. By the sound of it, Fred, we should keep doing that.
Yes.
No?
I think there might be arguments against that.
Yeah, probably are. Yes. Yeah. Don't do anything I say. It's usually wrong. But thank you very much, Greg, for sending in your question. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Okay, Fred, we've got a couple of audio questions, so let's get into those. The first one comes from Switzerland.
Hello, Fred and Andrew. This is Michael from Switzerland. I have a question for you regarding the Artemis 2 mission. So there it is claimed that they have visuals of meteorite impacts on the moon's far side. So my question is, how do we discriminate these one-person sightings from physiological impact of high-energy radiation with the human retina in space? One-person visual, to my knowledge, is not a scientific evidence, so you need at least 2 or more individual sightings of the same event, or at least a technical sighting. So what is your opinion on that? Because this makes big wave in the community, and I'm not sure whether they really have seen meteorite impact or just were fooled by their own sight. Thank you for answering, and love your show. Bye-bye.
Thank you, Michael. I mean, It's a good question to ask, because all I've heard is that there were 4 astronauts on Artemis 2 that went around the moon. As far as I'm aware, and I've just double-checked it, all 4 of them witnessed this event. So it wasn't just one, as far as we're aware.
It's a bit more complicated than that, Andrew.
I suspected it would be.
Yeah. So there were the crew of 4, and 6 impact flashes were observed.
Mm-hmm.
And I think there is a breakdown, which I have had but can't lay my hands on it, as to, here we are, yeah. Reed Wiseman was the commander. He saw 2 impacts. Jeremy Hansen observed another 2. And I think also the other 2 crew members observed some. But the bottom line here is,
they only saw them one at a time.
Were they seen together? And once again, my AI assistant says the specific number of flashes definitively witnessed by more than one astronaut at the exact same moment has not been isolated from the total tally by NASA. So we don't know whether any of them saw the same, more than one of them saw the same flash. And in that regard, Michael's got a very good point, I think, because one visual sighting isn't really a scientific observation. It needs to be somehow corroborated. And, one way of doing that would have been photography, but I don't think there were any photographic or imaging records of these flashes. So I think he's right to raise the question, because we do know that subatomic particles, and this is particularly cosmic rays, pass through the body and can essentially give you a flash on the retina as they go through one of your retinal cells. They can basically excite it, and you see a flash of light. I'm pretty sure I've seen them myself, a single flash against a black background. Certainly the electronic detectors that we used to use at Siding Spring Observatory, they're probably better these days, were very susceptible to these cosmic ray events. So when you took an image, you found that a lot of flashes, sometimes lines where the cosmic ray has gone, actually entered in the plane of the detector. So it's gone through many pixels and excited them all. So it's a real phenomenon. Now, my instinct would be that there might be a differentiation in the duration of these flashes, because cosmic ray flashes on your retina are extremely brief.
Yep.
But I think the flashes observed by the Artemis astronauts were also extremely brief, in the region of milliseconds, probably. And that's... you probably would not be able to tell the difference between one and the other. And again, they're in a high radiation environment. They are on the in orbit around the moon. They are shaded from the radiation field of the sun, the direct radiation field of the sun, because the moon's in the way. They were looking at these on the dark side of the moon. But the cosmos as a whole was open to them, and that's where cosmic rays come from. They come from the universe generally. So I think Michael raises a good point, and it's one, it'd be nice to, get a bit more knowledge of this to see if we can get some eyewitness accounts from the Artemis astronauts. They may be writing their memoirs or whatever at the moment. It would be very good to see if any of them can corroborate these millisecond long flashes of light.
Yeah, it says a lot, though, about the sensitivity of the human eye, though, doesn't it?
It does, yes. Yes, well, it all does. We think there have been experiments done quite some time ago that suggests that the human eye can almost detect individual photons.
Yeah.
Kind of, perhaps groups of 5 or something like that. detectable. I can't remember the details of it, but yeah, a well thought out question from Michael there, and one to which we don't really have the exact answer.
No, I suppose if they do write a report or something, they might be able to clarify what exactly was seen and who saw it and how many of them at the same time, etc.
Yeah.
But if it turns out that they only each saw this phenomenon individually, then probably it remains just a casual observation. It's not a scientific thing.
That's correct. Yes, exactly.
All right. Great question, Michael. Well done. And thanks for sending that one in.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem. We've had a main B plus undervolt.
Roger, main B undervolt. Okay, stand by, 13. We're looking at it.
Space nuts.
Our final question today comes from somebody who forgot to tell us their name.
Hi, guys. I've been listening to the show for many, many years. I'm a Brit, obviously. I've been wondering about how to ask a question. I've had several questions in the past. The question I have now is there anything else that I haven't found that is going to go and observe the sun at such, or even at a longer thing? Because my favorite spacecraft in the world is the Parker Solar Probe, and I think it is done such an amazing job, and I was just wondering if there was anything else that you guys knew that might be more exciting. So there we go. Anyway, thank you very much for this. The podcast has been fantastic for me. It's kept me going through several nights, months, and years, and that was the best question I could come up with.
Fair enough, and it's a good one. Thanks for sending it in. Don't know your name, but we know where you are. We know where you are. Now, he mentioned the Parker Solar Probe. That's also achieved the fastest speed by a human-made object ever, I think, fairly recently. Yeah. There are several probes out there sort of doing the solar thing, the Solar Orbiter, which is an ESA mission. There's also the Solar Dynamics Observatory, although is it up there or is it on Earth? I can't remember. It's a NASA observatory.
Yep.
SOHO, the Solar and Heliospheric Observatory. Stereo, we've talked about Stereo. It's two spacecraft orbiting the sun from different angles so that they can get a 360-degree view of the star. And the JAXA NASA mission Hinode, that's
right.
Yeah, which is focusing on magnetic fields. So they're the ones that I'm aware of at the moment. Are they more exciting? I suppose in their individual ways, they've all got something different to contribute. So they'd all be exciting in one way or another.
That's right. And there are some upcoming ones as well that I think qualify for being exciting. But just to, backstory of the Parker Solar Probe, the reason why it goes so fast is that it comes so close to the sun.
Yeah.
And anything that's in orbit, and an elliptical orbit, is at its fastest when it's at perihelion, the nearest point to the sun. And in fact, that near point takes it through the sun's inner corona. And I think I read that this last week it had its, was it its 28th flyby of the solar corona? I think that's right. It's on the 11th of June, it completed its 28th close approach to the sun. Sorry, on the 8th of June, matching its record distance of 3.8 million miles, or about 5 million kilometers, something like that. So that's why that's exciting, because it gets fried nearly every time it goes that close to the sun. But I think there are some coming up which are also pretty exciting. ESA's Vigil spacecraft, which will launch in 2031. That's going to be at the L5 point, Andrew. So it's one of the two Lagrange points which shares the same orbit as the Earth, and it's actually the one behind the Earth in terms of the way the Earth circulates in its orbit. So it's 60 degrees behind the Earth, And what it sees from that vantage point is a different view of the sun, because it sees the side of the sun that is invisible to us, but is about to become visible as the sun rotates. So it will see the sun several days before it moves into our view from Earth. So what it's doing is giving you advanced warning of all the kind of activity that we see on the sun's surface, coronal mass ejections, solar flares, all of that stuff will be visible before it comes into our before it points towards the Earth, where some of these things could actually have an effect on us on Earth. There's something called Proba 3, which is 2 satellites. And this, I think, is pretty exciting as well. They're in Earth orbit, but they basically give you an artificial eclipse in space.
Oh, wow.
So you have one which is shaped like a disc in as much as you can see it in the direction towards the sun. That sits in front of the sun. The other one's some distance behind, and the two of them actually let you see the inner corona of the sun. So that's also exciting. That I don't know when that's planned to be launched. But I beg your pardon, that is already in orbit. That's one that's already in orbit.
Okay.
It's a very highly precise formation pair of satellites. I think we've talked about it before, actually. Now I come to remember.
Sounds familiar.
Yeah, and then once again, another there's a NASA set of satellites called Punch, 4 satellites. Which basically are in what's called a sun-synchronous orbit. They're always moving along the line between day and night, and again that will give us 3D observations because there are 4 satellites and they're in different places. There's going to be an Indian one. I think there's all sorts of really exciting stuff coming up for solar astronomy, which we'll learn from a whole new fleet of spacecraft. So once again, I'm sorry, I don't know your name, but it's a good question and a great one to ask.
Indeed. And not forgetting all the land-based solar observatories, and one that I've seen that I visited there last year, or drove past it anyway, was on Mount Teide in Tenerife.
Yes.
It's a solar observatory, the Gregor Observatory, I think.
I think that's right, yes. And there's also the Daniel K. Inouye telescope, which is on the summit of Haleakala on Maui. We got married in front of it, Marnie and I.
Yeah.
And that's the biggest solar telescope at the moment. I think there's a bid to try and build a bigger one, but the Daniel K. Inouye telescope, a 4-meter telescope looking at the sun. So we've got the most exquisite detail on the sun's surface coming from that telescope.
You can't keep China out of it because they've got the Chinese Large Solar Telescope, which is quite a big one. And the list is long. There are many on the actual surface of the planet that are dedicated to solar observatory. So, and for the record, the Parker Solar Probe achieved the fastest speed by any human-made object on the 24th of December 2024, when at perihelion it achieved a speed of 430,000 miles per hour, which is 692,000 kilometres an hour. And yes, everyone's been arrested now.
Quite right, too.
Yes. That's extraordinary speed, though. It really is. Quite an amazing feat. But thanks for sending it in, your question, whoever you are, but we know where you live. And that brings us to the end. Fred, thank you very much.
Pleasure, Andrew. Good to talk again, and we'll speak again soon, I hope.
We will indeed. Professor Fred Watson, astronomer at large, and if you would like to send a question in for our Q&A episodes, please do. Just go to our website, spacenutspodcast.com, spacenuts.io. Click on the AMA link at the top where you can send text and audio questions, and we'll do our very best to ignore them. But then again, we'll probably answer them. Sometimes we get people that double up and triple up and So if we don't answer your question, it's probably because someone else already beat you to the punch. But, I do my best to go through them and make sure we don't miss anybody. But, yes, I try to share it around so it's, different people all the time as well. So, there's all these bureaucratic things I've got to deal with. And thanks also to Hugh in the studio. Now, our last question came from a fellow who said he was looking into how to ask a question, and that got Hugh thinking. So he went to look it up, and he's still trying to figure out how to ask a question. That's why he couldn't be with us today. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.